Hello friends, this is the last part of this video series on GATE 2016 Power Tonic Solutions. Now we are left with 4 questions. Let's go and solve them. So this is question number 44. This question came in GATE 2016 set number 6 and it is related to inverter circuit. The switches T1, T2 in figure A, so this is switch T1 and T2, are switched in a complementary fashion with sinusoidal pulse width modulation technique. The modulating voltage VMT is equal to 0.8 sine 200 pi t. So the red waveform you can see here is the modulating voltage waveform. So VMT has peak magnitude of 0.8 into sine omega into t. So this is omega. So the frequency of modulating voltage waveform f of m is 100 Hz. And the triangular carrier voltage Vc. So these high frequency triangular wave you can see in figure B, it is carrier voltage Vc waveform. So they are shown in figure B. The carrier frequency is 5 kHz. So the frequency of carrier, which is high frequency triangular wave, is 5 kHz. The peak value of the 100 Hz component of the load current IL in ampere. So we have to find the peak value of 100 Hz component in IL. Let's call it VAB. So we need to find 100 Hz component in VAB. So when you get it, you can easily divide it by impedance to get what is IL. So this inverter is using sinusoidal pulse width modulation technique. It means whenever your modulating signal is greater than carrier, T1 is on, and whenever Vm is less than Vc, T2 is on. So when T1 is on, VAB is equal to, so when T1 is on, VAB is equal to VDC by 2, and when T2 is on, VAB is equal to minus VDC by 2. So for sinusoidal pulse width modulation technique, you know that VAB is equal to M, which is modulation index, and your voltage is moving from plus VDC to minus VDC by 2. So it is M VDC by 2 into sine of, and it is in phase with your modulating signal. So it is 200 pi t. So what is M is modulation index is nothing but peak value of modulating signal divided by peak value of carrier signal. So peak value of modulating signal is 0.8 volt and peak value of carrier signal is 1 volt. So modulation index is 0.8. And you know VDC by 2 is 250 volt. So you can put M and VDC by 2 here. So this is VAB 100 Hz component. So to get IL 100 Hz component, you need to divide VAB by Z at 100 Hz. So right now we are interested only in the magnitude of IL. So I am ignoring what is the phase of impedance Z. So here you can see Z at 100 Hz is 12 plus J16. This is the impedance at 100 Hz. So let us put Z here. So the magnitude of 12 plus J16 is 20. So it is 10. sine 2 pi into 100t, plus it will contain some phi. It depends upon z. So the question is, what is the peak value of 100 Hz component? So it is 10 amp. This is the answer for this question. This is question number 46. This question came in GATE 2016, set number 8, and it is related to inverter circuit. So we have a three-phase voltage source inverter as shown in the figure is feeding a delta connected resistive load of 30 ohm per phase. If it is fed from 600 volt battery with 180-degree conduction of solid state devices, the power consumed by the load in kilowatts. So we have to find what is the power consumed by this three-phase delta connected load during 180-degree conduction of voltage source inverter. So let us draw this three-phase circuit again to get better understanding. So we have an input voltage source of 600 volt. Then we have three-phase voltage source converter. Here is three-phase delta connected load of 30 ohm per phase. These are anti-parallel diodes of each switch. Let us name these switches as S1, S3, S5, S4, S6 and S2. So this is A phase, B phase and C phase. So now we have to find what is the power consumed by this three-phase delta load. So we can use the single phase technique to solve three-phase circuit. So what we can do is we can find what is the power consumed by this load per phase, and once we get per phase power, you can multiply it by 3 to get total three phase power. So to get per phase power, we need a voltage VAB. So let us call the return of battery voltage as N. So VAB is VAN minus VBN. So now you need to get what is the potential of A with respect to N and what is the potential of B with respect to N. You can subtract these two to get VAB. I am doing in this way because it is easy to get VA and VBN, because you know that when switch S1 is on, VN is VDC, which is 600 volt, and when switch 4 is on, VN is equal to 0 volt. So let us write this. So VAN is equal to 600 volt when S1 is on, and it is 0 when S4 is on. Similarly, VBN is 600 volt when switch 3 is on, and it is 0 when switch 6 is on. So let us draw the gate signal and phase voltage of this three phase voltage source converter. So this is time axis omega t. So these vertical lines are at 60-degree interval. 2 pi by 3, 4 pi by 3 and 5 pi by 3. So first I will draw gate voltage of switch 1 and switch 4. So this is 1, this is 4. So as this it is 180-degree conduction. So for from 0 to pi, switch 1 will conduct. So here 1 is on, and from pi to 2 pi, 4 will conduct. 4 is on. Similarly, you can draw switch waveform for phase B. So this is switch 3 and this is 6. So gate voltage of 3 and 6 will be similar to 1 and 4, but it will be 120-degree phase shifted. It will look something like this. So from 2 pi by 3 to 5 pi by 3, 3 is on, and from 0 to 2 pi by 3, 6 is on, and from 5 pi by 3 to 2 pi, 6 is on. So now you know switching gate signal of switch 1, 3, 4, 6. So you can easily now draw what is VAN. So you know that when switch 1 conducts, VAN is equal to 600 volt, and when switch 4 conducts, VAN is equal to 0 volt. So from 0 to pi, switch 1 is conducting, so VAN is equal to 600 volt, and then it is 0. Similarly, you can plot VBN. So when switch 3 is on, VBN is equal to 600 volt, and when switch 6 is conducting, VBN is equal to 0. So this level is 600 volt. Now you need to find what is VAB. So VAB is nothing but VAN minus VBN. So you can subtract these two waveform. So VAB. So from 0 to 2 pi by 3, VAB is equal to 600 volt. And from 2 pi by 3 to pi, VAB is 0. Then from pi to 5 pi by 3, VAB is minus 600 volt. And from 5 pi by 3 to 2 pi, VAB is 0. So now you know what is the voltage waveform of VAB. So from here you can easily calculate what is per phase power consumed by the load. So here is the voltage waveform of VAB which we found out. So from here you can easily calculate what is the power per phase consumed by this 3-phase delta load. So you know that average power is 1 upon time period 0 to t VI dt. So the time period here is 2 pi. You can break this integral from 0 to 2 pi by 3 VI dt, then from pi to 5 pi by 3 VI dt. So you know that voltage is 600 volt and current is nothing but V by R, so it will be 600 square divided by 30. Similarly from 5 pi to 5 pi by 3, it is 600 square divided by 30 dt. So it is 1 by 2 pi. You can take 600 whole square divided by 30 outside. So it will be 2 pi by 3 plus 2 pi by 3. So 600 whole square divided by 30, 1 by 2 pi into 4 pi by 3. So this is 600 whole square divided by 30 into 2 by 3. So pi will cancel. So this is power consumed by per phase. So power consumed by total three phase delta load is P15 into 3. So 600 का whole square divided by 30 into 2 by 3 into 3. So it will come to 24 kilowatt. And this is the answer for this question. This is question number 48. This question came in GATE 2016 set number 8 and it is related to inverters. So we have a single phase bidirectional voltage source converter is shown in the figure below. All the devices are ideal. It is used to charge a battery at 400 volt with power of 5 kilowatt from a source Vs 220 volt RMS 50 Hz sinusoidal AC mains at unity power factor. So we have a voltage source 220 volt RMS and the power factor here is unity. So we have unity power factor. If its AC side interfacing inductor is 5 millihenry, so we have a 5 millihenry inductor which is interfacing this voltage source to the inverter, and the switches are operated at 20 kilohertz. The phase shift delta between AC mains Vs and fundamental AC RMS voltage source converter in degree. So we have to find the voltage shift between this Vs voltage source and fundamental AC RMS voltage source converter. So this is VC. So we have to find the fundamental voltage component of VC. VC is the input to the voltage source converter. So let us draw this circuit again. So we have a sinusoidal source of 220 volt RMS 50 Hertz. Then we have an interfacing inductor 5 millihenry, and we have single phase voltage source converter. We have 1 millifarad output capacitor and a battery of 400 volt. So we are charging this battery from 220 volt 50 hertz sinusoidal AC source. So as this voltage converter is bidirectional, so it means that power can flow from the input to the output side and vice versa. So right now power is flowing from the input side to the output side. This is the power flow direction. And this voltage source converter is working as a diode based rectifier. So this is VC. Now we have to find the fundamental component of VC. Let's name the switch S1, S2, S3, S4. So we know that output power, so this is P out, is 5 kilowatt. So as all the devices are ideal, so output power must be equal to the input power. This is input power. So P in also should be equal to 5 kilowatt. Now what is P in? We know that here power factor is unity. Let's say this current is IS. This voltage is Vs. So Vs into Is into power factor is 5 kilowatt. So what is 5? It is nothing, the angle between Vs and Is. So phi is 0, that means cos phi is 1. So from here we can get the RMS value of input current, which is 5 into 10 to the power 3 divided by voltage source RMS, that is 220. So this is the RMS value of the input current. So now if you apply KVL in this loop, you can write minus Vs plus L dis by dt plus Vc is equal to 0. So Vc is equal to Vs minus L dis by dt. So we are interested in the fundamental component. So we can write VC1. So the fundamental frequency is 50 Hertz. So now we need to take the fundamental component in voltage source, divide inductor, and the fundamental component in the current. So we know that Vs1 is root 2 into RMS value into sine of omega t. Inductance value is 5 millihenry to d by dt of is1. So we know that is1 is root 2 into RMS value. We have calculated here RMS value 220 into sine omega t. It will be in phase with your voltage source because the power factor is unity. So put this equation here, you will get, so differentiation of sine omega t is cos omega t into omega. Now omega is, as you are calculating fundamental components, so omega is 2 pi into 50. So upon solving this equation, you will get 311.12 sine omega t minus 50.48 cos omega t. So now you can use trigonometry here. So let's consider this size at 50.48, 311.12, and from Pythagoras we can calculate this as 314.99. So this is theta. So if you multiply and divide by the hypotenuse, you can get, so this you can write it as cos theta sine omega t minus sine theta cos omega t into 314.99. So this thing you can write it as 314.99 sine of omega t minus 9.21 degree. So this is the expression of VC1. So now we know that Vs is root 2 into 220 sine of omega t, and VC fundamental component is 314.99 sine of omega t minus 9.21 degree. So if you draw phasor, so this is the fundamental component Vs, and so you can see the phase difference is 9.21. It is lagging, and this is equal to delta. So delta is equal to 9.21 degree. This is the answer for this question. This is question number 45. This question came in GATE 2016, set number 8, and it is related to AC to DC conversion. So we have a full bridge converter supplying an RLE load is shown in figure. The firing angle of the bridge converter is 120 degrees. So the firing angle of this thyristor full bridge alpha is equal to 120 degree. The supply voltage VMT is 200 pi sine 100 pi t. So the supply voltage is here. R is 20 ohm. E is 800 volt with this polarity minus plus. The inductor L is large enough to make the output current IL a smooth DC. So the load current is a smooth DC current. Switches are lossless. Now we have to find the real power fed back to the source in kilowatt. So we have to find what is the real power fed back to the source by this RLE load. So let us draw this schematic again to get better understanding. We have input voltage source VMT, and we have a thyristor bridge which is feeding a RLE load. L is large enough here so that the load current IL is a smooth DC current. So it is a IL is a smooth DC current, means that anytime two of the four thyristor will conduct. So VMT is equal to 200 pi sine of 100 pi t, and the alpha is 120 degree, which is 2 pi by 3. Let us name this thyristor as T1, T4, T2, and let's say this is T3. So now I will draw some waveforms to know how is this converter working, and I will plot this voltage VAB. So now you can see that whenever T1 and T4 conducts, that is T1 and T4. So whenever T1 and T4 are conducting, VAB will be equal to Vm of T. You can get this by applying KVL in the circuit. So this is when T1 and T4 are on, and VAB will be equal to minus VMT when T3 and T2 are on. So let us go and draw some waveform. So first I will draw Vm and minus Vm, that is input voltage source. So it is a sinusoidal voltage source. So minus will be this negative of it. So this is minus Vm of T. The yellow one is Vm of T. X-axis is omega T. This is pi by 3. This is 2 pi by 3. 4 pi by 3. 5 pi by 3. So at omega T is equal to 2 pi by 3, which is the firing angle. Here I am giving gate signal to T1 and T4, and at omega T is equal to 5 by 3, we are giving gate signal to T3 and T2. So from omega T is equal to 2 pi by 3 to 5 pi by 3, T1 and T4 are on. Similarly from 0 to 2 pi, T3, T2 are on, and from 5 pi by 3 to 2 pi, T3, T2 are on. So let us plot VAB. So I told you whenever T1 and T4 are on, VAB is equal to Vm of T. So you have to just copy it. and when T3 and T2 are conducting, VAB is equal to minus of VM. So VAB has a time period of pi. So let us go and calculate what is VAB average. This is nothing but 1 by T 0 to T VAB dt. So we have time period of 0 to 2 pi, 0 to pi B of AB and d omega t. So you can take this interval into 0 to 2 pi by 3. So 0 to 2 pi by 3 VAB is equal to minus of VMT. So it will be 200 pi sine of 100 pi t into d omega t, and from 2 pi by 3 to pi VAB is equal to VMT. So you can take 200 pi outside the integral, and if you integrate minus sine omega t, it will give cos of omega t, limit 0 to 2 pi by 3. Similarly, you can write minus cos of omega t, limit 2 pi by 3 to pi. So pi will cancel out, it will be 200. Now cos of 2 pi by 3 is minus half. So this and 1 and minus 1 will cancel out. So what you will get is VAB average minus 200 volt. So let's go back to the circuit. So now we have got VAB average value. So you can draw equivalent circuit considering VAB average and RLE load. So let's go and draw this. Now you have VAB average and RLE load. Let's say current is I. So you know that under steady state, the voltage across inductor VL average will be 0. So now you can apply KVL in this circuit. So minus VAB average plus voltage across inductor average plus I average into 20 ohm minus 800 volt is equal to 0. So minus VAV average, so VL average is 0, or you can write IL average is equal to 800 plus VAB average divided by 20. So we found that VAB average is minus 200 volt. So IL average is 30 amp. So now you have to find what is the power which is fed back to the source by this RLE load. So you can notice that your actual VAB average is something like this, because we are getting minus 200 volt. So the voltage polarity is like this, plus and minus, and current is going into the plus polarity. So you can write power fed back to the source, average power is equal to IL average into VAB average. So IL average is 30 amp into VAB average is 200 volt, which will be equal to 6 kilowatt. This is the answer for this question. So please like my Facebook page Triple E Helper. I will post this video on this page. If you want, you can share with your friends. And also subscribe to my YouTube channel for more videos. And if you have any doubt or query, you can either mail me or you can write in comment section of this video.